Okay, I just go back to discuss why mm, I should say that why uh, we can see what is the imbalance issue here. Uh, usually the batteries are series connected together. Okay, the batteries are series connected together, and when we charge the battery or discharge the batteries, the current through each cells might be the same because they are series connected. Okay, so the charging current, the discharging current for every cell should be the same. Then we expect that because the current are all the same, so the state of charge of all the cells should be identical. But it is not. Even though the current through the cells are the same, the SOC state may not be the same. This is a problem. Um, Here, this is an example. Uh, in this figure, there is an example, and this example is four series connected lead acid batteries. This is lead acid batteries. Last week we discussed this kind of battery. The, it can tolerate the overcharge and discharge. I said we can abuse the batteries, the lead acid batteries. So here in this case, we can see this one, this gray one. The voltage when we discharge the batteries, the voltage decreases. Okay, but this one, it decreases even more than all others. And when we charge the batteries, this one increase much higher than others. The reason is basically this battery cell has much less capacity than others. The SOH of this battery is less than others. So when we discharge a battery, this cell decreases most. And when we charge the batteries, the voltage of this cell also increase more than others. Okay, but this is lead acid battery, so the overcharge or over discharge will not result in any hazard, any dangerous hazard here. If this is lithium ion batteries, the over discharge here will damage your battery. The overcharge here may cause explosion. So this is different. For lead acid battery, this is fine. It is safe. It is still safe, but maybe the battery will be damaged. But that's fine. That's fine. There is no immediate danger here. But for lithium-ion battery, this is not allowed. Okay. So for the lithium-ion batteries, we have to prevent this kind of overcharge and overdischarge. Okay. But anyway, the imbalance of the cells happens. Okay. And here I just want to say that the SOC and the voltage are closely related. Here, this is a stabilized open circuit voltage. That means the cells there is no current through the cells. Okay, there is no any current through the cells, no charging, no discharging. And it is stabilized means it is put there. The battery is put there and charged for a long time, so the voltage is stabilized. For the stabilized open circuit voltage, this voltage is very closely related to SOC here. This is discharged by different current rate. Okay, no matter high current rate or low current rate, after the battery is stabilized, the voltage and DOD and also SOC, okay, they are on the same curve. It's not linear, okay. It is not linear, but but the voltage is still related to the SOC. And this is under different temperature. Okay, under different temperature, we just discharge a battery and stabilize them. Then the voltage and the SOC are still very close. Okay, so usually we can use the voltage to substitute the concept of SOC. Okay, they are almost the same. They are almost equivalent in our language. And here, you see the battery system. For the battery system, there is some imbalance there. And when we charge the battery, if these batteries are lithium-ion batteries, as I said, we cannot overcharge the batteries. Okay, so when we charge the batteries, you see, this is almost full. So we cannot further charge the battery anymore because this cell is full. If we keep on charging the battery, this is overcharged and might explode. Okay. So it is limited. The charging is limited by the highest SOC cell. Okay, and when we discharge the battery, you can see the cell here has a very low SOC. Okay, again, we cannot over discharge the battery cell, so the discharge will be limited by this cell. Okay, so if for this very extreme case, the usable capacity of the battery pack actually is very small. Even though actually there are some cells that still have the charge capacity, but we cannot further charge or discharge the battery. Okay, so if the imbalance happens in your stream, it is very possible to reduce the whole capacity, the capacity of your whole battery pack. It is very likely to happen. Or if your charging protection or discharging protection function is not function well, then overcharge or over discharge may damage the system. That is also not favored. Okay, both the cases are not favored here to limit the capacity or damage the battery. They are bad for our system. So we have to make the balance, the cells to be balanced to prevent these issues. Okay, so the problems of the unbalanced battery system may cause overcharge, may cause over discharge, or may cause less useful energy for your systems. And the imbalance will be more serious, even more serious after several numbers of cycles. That means if the imbalance happens, then you charge and discharge your batteries cycles by cycles, and after a few cycles, the imbalance will become more serious. Okay. It will not recover. The imbalance will not recover by itself. It will become more. It will become worse. Okay. Why there is an imbalance? Okay. First is manufacturing tolerances. That is, after the battery cells are manufactured, there are some differences in the cells. Okay. So there is intrinsic tolerances in the battery cells. And second, the uneven temperature distribution. In the battery pack, we cannot expect that all the temperature inside the pack is all even. Everywhere the temperature is the same. We cannot expect that. But the temperature will influence the capacity of the batteries, you know. So the uneven temperature distribution will cause an uneven battery capacity and make the battery to be imbalanced. Okay, so this is another reason. And then the backpack or module assembly. You know, when we assemble the cells into module or pack, we have to solder. We have to connect them together, but the connection maybe not so generous, not so homogeneous. Then for some connections there is higher impedance. For other connections, the impedance is lower. So the charging or discharging may be easier or more difficult. So that will cause some imbalance on the connections, and maybe the aging rate is different for each cell. Okay, so there are many reasons for the imbalance, and we cannot just expect all the cells are even. We cannot expect that. We will expect in a few cycles, all the battery pack will become imbalanced. So we have to take some actions to prevent this to happen. We just said that there are three methods. Okay, there are three categories of the charge balancing actions. First one is to waste the energy. We also said this is the energy dissipation method. We just dissipate the energy, the excess energy, by resistor. And I said this sounds very weird. We just waste the energy, but you have to know that this is a very effective method. This is an effective method. That is by this way, we can easily make the SOC of the cells to be even. It is very easy. Okay, we don't have to produce a very complicated circuit. We just use a resistor. We can do this function. Okay, so this is effective, and this is actually very popular. This is very popular, especially for the cells, for the module level. For the module level, in the module, if we want to balance the cells inside the module, this method is very popular, applied. And the second is energy transfer. Transfer the excess energy from this cell to the other cell, okay, to make them even. And the third one is to control the energy. To control the energy means when we charge it, we give the less SOC cells more charge, and give this one less charge. When discharge, just the other side. Okay, how to implement the energy dissipation? It's easy. We just connect the resistors to the battery. Okay, connect resistor to the battery, but there still is switches there to actively control the dissipation of the resistors. You know, basically, if we just ignore the switches here, we just parallel every battery cell with the resistors. And of course, the resistance of the resistors should be the same. Okay, the resistance should be the same. And you know, when the SOC of some cell is higher, we can also expect the voltage of the cell is also higher, right? So if we just simply parallel each cell with the same resistor, then we can expect if the SOC is higher, the cell's SOC is higher, the cell will dissipate more energy on the resistor because the voltage is higher. And we know the energy will, the power, the dissipated power will be V squared over R. And now we have the same R, and the higher voltage will result in more dissipated energy. So, if we don't have the switches, this method can still achieve the balance function. Okay, but we have to equip the switches here. That is, we don't want to dissipate the energy anytime. Okay, we do not want to constantly dissipate the energy. We only want to dissipate the energy when it is necessary and when it's necessary. Usually, we will only dissipate the energy to achieve balance when we charge the battery. Okay? I think this is very reasonable, because when we use a battery as a power source, if in the same time the resistors are dissipating the energy, then the usable capacity is reduced. So when we discharge the battery, we will disconnect all the switches. So when discharge the batteries, we do not do the balance action. Okay, so only when we charge the batteries and when the battery voltages are higher than some threshold, then we activate the switches. And we can only activate the batteries of the highest SOC or higher SOC to dissipate the energy by the resistors. Okay. So even this is an energy dissipation method, it is very easy. The BMS IC still have to control it, still have to monitor the battery SOCs and decides which battery should be dissipated. Okay. And usually the BMS IC will equipped with its intrinsic switches. Okay, so and the BMS IC itself can turn on the switch here and dissipate the energy from the cell. Okay, and it can control which one to activate. So, so it is. I said it is very popular. It is very effective. Okay. For the energy dissipation, only one method. There is only one method. Okay. But for the other categories, there are many methods. So then I will spend a lot of time to explain the different methods. And this is now starting from now, I am talking about the energy transport category. Okay, now there are energy transfer. And the energy transfer, we have to transfer the energy by some medium. Okay, we have to transfer the energy by some medium, and the medium will be the temporary energy reservoir. The energy reservoir, you can think of maybe the capacitors. You know, the capacitor can temporarily store energy, or the inductor can also temporarily store energy. So later we will use the capacitor and the inductors to be the media to transfer the energy. And here we use a capacitor to transfer the energy. The circuit is like this. Okay, the circuit like this. If there are n battery cells, then the capacitor number will be n minus 1. The number of the capacitor is one less than the battery numbers. Okay, and the switches here can be attached to the upper terminal or the lower terminal, and the operation of the switches are unified. If all the switches are attached to the upper terminal. Then you can see the capacitors are attached to the upper battery cells. And the the voltage of the capacitor will be aligned to the battery cells. Okay, so here the battery voltage, the capacitor voltage is like this one, and this capacitor voltage is like this one. And then we just switch we just reconnect the switch to the lower terminal. Then the capacitors are attached to the lower batteries, and then you can find that because originally the capacitor voltage is lower, okay, so the battery will supply its charge or energy to the capacitor. And also the same situation happens in this capacitor. So the battery cells will charge the capacitors in this state, and then the switches are connected to the upper terminals again. So at this time, the capacitor voltage actually is higher than this one. So the energy will be transferred to this battery cell, and this energy will transfer to this battery cell. Okay, so by this way, it is very easy. The switches are alternatively connected to the upper terminal or the lower terminal. We don't have to control anything. We just constantly change the switches to the upper or lower terminals. That's fine. So the advantages of this method is no sensor or heavy computation burden are required for this method. Okay, the control for this method is very easy. Okay, so it is very easy to implement, and the loss is limited because basically the capacitor do not dissipate energy. Basically, but of course you have to understand that the switch operation and there is some equivalent resistance on the capacitors and the trays. So there still is some loss. Happens when we transfer the energy, but it's less than the previous method. Okay, and there are some disadvantages. First, this method can only transfer energy between the neighbors. It can transfer energy from this one to its neighbor, this one. Only the neighbor to neighbor transfer is possible. Okay, so if we want to transfer the energy from this end to the other end, it takes some transference operations. Okay, not only one transfer. Several transfer is required for the energy from this end to the other end, and it will be even worse when the cell number is higher in the battery pack, in the battery module. Okay. And the second disadvantage is the equalization speed is very slow. The equalization is very slow. The slow equalization speed, there are two reasons. One reason is only neighbor-to-neighbor transfer is possible. So it takes several transference for the energy to reach its end. It takes time. Okay, but this is not the most important reason for the slow equalization. You have to know that the energy transfer actually happens from the voltage difference on the neighboring cells. What I mean is, these two cells, they transfer energy via this capacitor, but the energy amount they can be transferred. Then actually it actually depends on the voltage difference here. If the voltage difference is higher, then every time we can transfer more energy via the capacitor. But now we want to balance the batteries. So finally, the battery voltage difference between the cells will be small. That is our target. So finally, the voltage difference will be small, but the small voltage difference will result in even smaller energy transfer. So this is an exponential. This is an exponential process. When we reach the target of the balance, the voltage difference is smaller and the energy can be transferred is also smaller. So the equalization speed actually becomes slower and slower. So the equalization actually will take a very long time. Usually for a normal system, it takes more than 10 hours to reach the balanced state. It is very normal, more than 10 hours. Okay. And the third disadvantage is current spike. You know, basically we can model the capacitor as voltage source. Okay, the capacitor is modeled as voltage source, and the battery is also a voltage source. And if we connect the two voltage sources together, you know, it is a violation of what? KVL. The violation of KVL actually will result in current spike. So for this method, there will be current spike, and the current spike eventually will damage the capacitors. Okay. So this scheme actually is only concept. This is only the concept, and to implement the switches, actually there are two switches here. Okay, two switches here. One switch connect to the upper end of the battery, and the other to the lower end of the battery. Okay, so for every switches here actually is implemented by two individual switches. And if we want to connect to the upper one, these two switches are turned on. If we connect to the lower one, these two are turned on. Okay. And there are several improvements on the capacitor-based equalizers. This one is easy because this is only to improve the current spike. Okay, here only want to solve the problem of the current spike. The method, the action here is the additional inductor connected to the capacitor, and because the inductor there, the inductor will smooth the current, you know. So the additional inductor will reduce the current spike. Okay, this is this improvement, and this improvement is I just said the energy or charge transference only happens between the neighbors, and here is a original system. Okay, this is a original system, and if we add a second tier capacitor here, then you can see for this capacitor, if the switches are connected to the lower terminal, then this capacitor is attached to these two batteries, and when the switches are connected to the upper end, then this capacitor connected to the upper two batteries. So by this second tier capacitor, actually the energy can directly transfer from this battery to this battery. Okay, so this is a second tier capacitor equalizer, and by the same method, we can extend to the three tier capacitor equalizer. Okay, they are the same method. And this one is called head to tail. And just now I said if I want to transfer the energy from this end to the other end, it takes several transferences. And by this method, we can transfer the energy directly from this one to that one. Here, by the action of the switches, the battery is connected to this capacitor, and then the capacitor is connected to this battery. So the energy can be transferred directly from this one to that one. So this is a head-to-tail capacitor. Okay, and the third improvement here, it is from the I just said the balance actually depends on the voltage difference of the neighboring cells, and unfortunately, the neighboring battery voltages, the difference will be smaller and smaller in the end. So here we change the operation. We change the operation of the switches. I take this one as an example. Okay. No. So here, when we charge the capacitor, okay, we transfer the energy from the batteries to the capacitor. Actually, we transfer two battery voltages to the capacitor. So the capacitor voltage will be equal to twice of the batteries. Okay, so the voltage here is higher than any one of the battery. Even though it is the final stage of the equivalent of the battery balance. Okay, it is in the end the voltage difference between V1 and V2 is very small, even though the capacitor voltage is the sum of the two batteries. And then if the BMS system find that the V2 has lower voltage, the voltage here is lower, then the capacitor will transfer the energy to the second battery or to the first battery if this one has less SOC. So by this way, the equalization speed can be enhanced. Okay. And this is the first improvement. The philosophy here is also different. By the switch operation, in the first stage, these switches are turned on. Okay, these switches are turned on on the first stage. The turn on of these switches will make the capacitors to be parallel to the battery cells. Okay, so at the first stage, the capacitors are parallel with the battery, so the capacitor voltage will be equal to the battery voltages. Of course, the capacitor voltage may be different, okay, because of the imbalance of the battery cells. And the second stage, at the second stage, these switches are turned on and the switches here are turned off. And the turn on of these switches will make all the capacitors to be parallel together. So at this stage, the capacitor energies will be transferred. The higher voltage capacitors will transfer its energy to the lower voltage capacitors. So at this stage, the energy is transferred, and then it comes back to the first stage again. The capacitors parallel to the batteries, and then the second round energy transfer. So by this method, the energy transfer is not limited to the neighboring batteries. The energy transfer actually happens in this stage, and all the batteries are participating. Okay, they are the capacitor-based equalization method, and here is a inductor-based. And this inductor-based, you can see that, for example, for these two battery cells, if we turn on this switch first, okay, turn on this switch first, then this voltage will charge the inductor, so there will be a current flowing clockwise. And then we just turn this switch off and turn on this switch. Then the current will flow this way, because you know the continuity of the inductor current will force the inductor current to flow in the same direction, and because this switch is turned off, the current has to flow this way to charge the upper battery cell. So we can transfer energy from this battery to the upper battery. Okay. Of course, in this method, we have to know the SOC of each cells and decide which switch to be operated first. Okay. The sequence of the switches will decide the current direction, will decide the energy transport direction. Okay. So this is the inductor-based equalizer. And for this method, also you can find that the energy transfer can only happen between the neighboring cells. Okay, only neighbor to neighbor energy transfer is possible, just like the original capacitor-based method. So if we want to improve this method, maybe we can take the same action as previously introduced. We have the first tier energy transfer, and we have the second tier and the third tier, okay, to enhance, to accelerate the energy transfer by multiple layers, multiple tiers. Okay, this is a philosophy. Okay, and this is another method. This method is, there is only one inductor here, and there are many batteries. Not like this. Here, there are many inductors. But the inductor components actually are heavy components, and they take some space. Okay, so if the size of your circuit is limited, if the weight is limited, so this method is not so suitable for your application. And here, this method maybe is better, because usually the active switches are light, and the active switches are, it takes little space. Okay, so here the weight and the size will be smaller because only one inductor is required here, and the operation will be if now I assume that this battery has a highest SOC, then we just turn on these two switches, and then the current will flow like this way. And then if I assume that the first battery has the lowest SOC, then we turn on these two switches, and of course we turn off these two, and then the current will flow in this loop. So the energy will be transferred from this highest SOC battery to this battery by this inductor. Okay, so by the in this way, there are many switches, but we can directly transfer the energy from the highest one to the lowest one. So it can effectively reduce the SOC imbalance in the battery module. And in this method, it is called S2M. Okay, it is called S2M, and the C2C here. S2M means I didn't Okay, here. S2M means string to module. String means a pack. And this is a module. Okay, here this is a module. This is a module. There are two modules in this example, and the two modules connected together to form the string. Okay, so this method is said is S2M and the C2C. C2C means cell to cell. There is a converter here. There is a converter here. This is a so-called LLC converter. Okay, this is called LLC converter. LLC converter means in this converter there are two inductors, the LR and the LM. There are two inductors and one capacitor here. So it is called LLC converter. This is a resonant converter. This is a kind of resonant converter. And why we need a resonant converter? That is because we have to understand that for the switching operation of the active switches, actually there is a switching loss. There is switching loss. And we hope to reduce the switching loss by the resonant converters. So by this converter, we can reduce the switching loss. So by this way, the transfer efficiency may be higher. Okay, this is the purpose. And here, this is the input of the LLC converter. Okay, and you can find that actually the input is a whole string. Okay, the input actually is a whole string, and this is the output. This is the output of the LLC converter, and the output can be connected to the module. Okay. The output can be connected to the module by the switches here. By these switches from K1 to K3 and KP1 to KP4. By the operation of the switches, the output can be connected to either one of the module. So it is called S2M. The energy is transferred from the string to one module. Okay, and you can find that here in this part actually is inductor-based equalizer, and there are two layers. Okay, and this can perform the cell-to-cell operation. So here actually is hybrid. There are two parts of the equalizing mechanism. One part is S2M, and this part is cell-to-cell. Okay, this module and this module. Okay, and this is introduction of the LLC resonant converter. Okay, there are two inductors and one capacitor here, and usually we need the switches. We need some switches to transfer the DC to the rectangular waveform and fed into the LLC resonant tank, and then the output will be the rectifier to transfer the AC signal back to the DC again and fade to the output. Okay, here it is not very similar because this is half bridge type. This is full bridge type. They are a little different, but the basic concept is the same. This is half bridge, and this transfer the DC voltage, because this is DC voltage. Transfer the DC voltage into the rectangular waveform and fed into the resonant tank here. And these two diodes are the rectifier. They transfer the AC back to the DC and fade to the modules. Okay. The advantage of the LLC resonant converter is first, it wants to achieve the zero voltage switching to reduce the switching loss, and second, it has a wider range of voltage gain. Okay, and the third, it makes use of the leakage and the magnetizing inductance of the transformer. If there is a transformer here, the leakage inductance and the magnetizing inductance can be used for the two inductors in this converter. Okay. and then is a converter best. Here we have several converters. Actually, they are identical converters. Here we use a buck boost converter. They are basic power electronics DC to DC converters. Here we can see if the battery here has the highest SOC, okay. If this has the highest SOC, then we turn on the switch here. And if we turn on the switch, then the inductor will be charged. So there will be a current flowing clockwise here. And then if we turn off this switch, okay, turn off this switch, then the current will be first to turn on this diode and flowing this in this loop. Okay, you can find this, and this operation is called the buck boost operation. By this operation, the energy can be transferred from this battery to its upper batteries. Okay, and however, then I can also say that if the B2 has the highest SOC, then we can also turn on S2. So we have the loop here, and when we turn off the S2, then the energy will be transferred to B1. For every cell, if we turn on the associated switches, the energy will be transferred to its upper stream batteries. Okay, everyone can be transferred to its upper batteries, but for B1 is the uppermost battery. It cannot be transferred to its upper batteries. So the mechanism will be different here. For B1, if B1 have the highest SOC, then we will turn on S1. So it will charge here, and then if S1 is turned off, then the current will flow in this loop. So for B1, it is different. For B1, it will transfer its energy to its downward batteries. Okay. Anyway, by the action of the converters, we can transfer the energies from one battery cell to the other battery cells. Okay, so we can do the energy transfer by this method. And here, this method is to apply the multiple winding of the transformers. There is transformer here, but there are several windings. And in this case, we have one primary winding, and several secondary windings. And for the secondary windings, the turns numbers are the same. All the secondary windings have the same turns number. Okay, and we can expect that when we operate the transformer, all the secondary windings have the same voltage. Okay, all the secondary windings have the same voltage because of the turns number are the same. Okay, so the voltage here will be the same. So when we turn on the switch S here, then the battery string will store its energy into the transformer, and then when the switch is turned off, the energy will be released by all the secondary windings. However, because the secondary windings have the same voltage level, and then if for example B1 has the lowest voltage, the SOC is the lowest, then the same voltage here, the lower voltage here, the current in battery B1 will be the highest. That means B1 will accept the most energy. So the energy is transferred from the whole string by this transformer, and then transferred more to the lowest SOC batteries. Okay, so by this way, we can achieve the balance of the battery strings of the battery cells. We can say this is a kind of string to cell, a string to cell equalization mechanism. We can also make it reverse. Now there are several primary windings and only one secondary winding. Okay, and the same, just like the previously explained the mechanism, we turn on all the switches. Okay, we turn on all the switches, and because the primary winding here, they have the same turns number, so the winding voltage will be all the same. And now, if for example B2 has the highest voltage, then B2 will transfer the most energy to the windings. Okay, and then when the switches are turned off, the stored energy inside the transformer will be released back to the whole string. So by this method, the highest SOC will provide more energy to the transformer and then receive the equally shared energy from the secondary winding. Okay, so again, by this method, we can achieve the balanced state. Actually, this topology is called a flyback converter. And this is cell to string. This method actually use the Class E inverter. Here is the Class E inverter, and yes, you don't have to worry too much. We don't have to understand too much about the Class E inverter. We only have to know. Class E inverter is a converter to transfer DC signal to AC signal, so it is an inverter, and it takes only one switch. It takes only one switch to fulfill the inverting function. Usually we need two more switches to achieve the inversion, but Class E takes only one. Okay, and Class E inverter also can achieve the zero voltage switching, so it can reduce the switching loss. Okay, so basically for this method is to achieve the soft switching to reduce the switching loss. And here we also transfer energy from the whole string. Okay, the whole string supply energy to this Class E inverter, and the inverter will transfer the energies to the secondary windings. And again, all the secondary windings have the same turns number, and then because of the difference of the battery voltages, the lower voltage batteries will accept more energy from the same secondary windings. Okay, so this is a method. Okay. In this method, it is called C2P and P2M multi-winding equalizers. C means cell again, and the P means pack, and the M means module. Okay. There are several modules here, and in this module, we can see we can just transfer the energy from this cell. If we turn on the switch here, then the energy from the cell will be transferred to the transformer here. And when this switch is turned off, then the energy will be transferred by this winding and this winding is connected to the whole pack, okay, because it is connected to the pack terminal plus and the pack terminal minus. Okay, so the cell energy can be transferred to the whole pack. So again, we can just if some cell has the highest SOC, then we can turn on its switch and transfer its energy to the whole pack. And we can do otherwise. Okay, we can do the other. We can do the other direction. The other direction is we can turn on this switch. Okay, we can turn on this switch. If we turn on this switch, then the energy will be transferred from the whole pack into the transformer here, and then transferred to the module. Okay, and when it transferred to the module, it depends on the SOCs of the cells. The lower voltage lower voltage cell will accept more energy. Okay. Okay, so this is one of the operation. If we turn on this switch, then the energy will be supplied from the whole pack. Okay, and then the energy will be transferred to the cells inside the modules, in these two figures. Okay, this is also a multi-winding equalizer. Okay, multi-winding here, and in this topology, we can decide which cell has the highest voltage and which cell has the lowest voltage, and we can operate like if B1 has the highest voltage, then we just turn on Q11 and Q12. Okay, then transfer energy here, and then turn off these two switches and turn on these two switches. Then energy will be transferred to this cell. So this is a cell-to-cell equalization method. It can directly transfer the energy from the highest one to the lowest one. So this is a very effective topology. Okay, I think we have to break here for a moment. Okay, so let's come back 5 minutes later. Okay. When we do the I myself have done the charge equalization of the battery strings for a few while, and at first, I think we have to reduce the number of the switches inside the circuit, the charge equalization circuit. We want to reduce the switch numbers, and we want to increase. Maybe we can use diodes or inductors or capacitors. However, we want to reduce the switch numbers at first, but later we find that actually we don't have to reduce the switch numbers. That is the consideration is like this. This is a method I proposed, okay, in a few years ago, and in this method, there are only one switch for each cell. Okay, one switch for each cell. Okay, so we reduce the switch number. However, by this method, we cannot directly transfer the energy to the target cell. I just said, if we can transfer the energy from this cell to the upper cells, but maybe in the end, I want to transfer the energy from this cell to, for example, this cell. But in this method, I can only transfer from here to all these cells, and then maybe this cell transfer to the upper cell and so on. It takes several times of transference. Then the energy can reach its target. Okay? There are many methods just like this, or you can find the inductor-based equalizer like this. We cannot directly transfer the energy to the target, and this method also. Okay, this capacitor-based method, they cannot directly transfer the energy to the target. So every time we have to, it takes several transference, and for each transference, it loses some energy because the efficiency always is not 100%. There always is loss for each transference. And if the transference number increases, the energy loss increases. Okay, so we hope to directly transfer the energy from this cell to that cell. That is from the highest SOC cell to the lowest SOC cell. That is the most effective energy transference method. So like this method, this is cell to cell. Or this method is also cell to cell. They can directly from the source to the target. They are effective. And here, we also try to find to propose the same philosophy. We want to transfer the energy from the source directly to the target. So we use a lot of switches. We call it selection switches or switch matrix. By the switch matrix, we can attach either one of the battery cell to the DC to DC converters. Okay, so in this topology, if for example this one has the highest SOC, then we just turn on the switch selection switches and connect this cell to the input of this DC to DC converter. And if this cell has the lowest SOC, we also turn on the switches and connect the cell to the output of the DC to DC converter. So we can directly transfer the energy from the highest one to the lowest one by the selection switches operation. Okay, and in this method, we have only one converter here and a lot of switches. However, of course, the switches have some cost, but the switches, by the operation, we can achieve the effective method, effective energy transfer. I think that is worth. Okay. And here is the same philosophy. Instead, the converter here is a bidirectional converter. Bidirectional converter means we can transfer energy from this side to the other side and the opposite direction. Okay, so we just divide the battery cells to two groups. There are two groups, and every time we choose the highest or lowest from either of the groups, and then connect them to the two ports of the bidirectional converters and transfer the energy from this side to that side. And every time we transfer from the source to the target. And by this topology, we just reduce the number of the switches to 1/2. Okay. And this is an implementation of the selection switches. Actually, it takes a lot of switches because you know, the switch, this is bidirectional, so the switch direction is also bidirectional. So for the bidirectional switches, it takes two switches at the terminal here. Okay, so this is the implementation. For the switch, if the inside the circuit there are several switches, one of the problem you have to think about is how to drive the switches. Okay, how to drive the switches. What I mean is, if these are MOSFET, then for each MOSFET we have to provide suitable VGS for the MOSFET. VGS means the gate to source voltage. Okay, we have to supply suitable VGS for each MOSFET. Then we can turn on the MOSFET switch. And unfortunately, for every source of the switches, the voltage labels are not the same. Okay, the voltage labels are not the same. So that means we cannot use one single voltage source as a driver voltage source. We need several voltage sources. And how to produce several voltage sources, that is a problem. Okay, so that is a question you have to fix. Okay. Okay, and this is also the application of the selection switches. Again, the batteries can be selected out and attached to one side of the circuit, and the circuit here is only one energy reservoir. The energy reservoir consists of inductor and the capacitor, so it can temporarily store energy here. So the operation is like this. For example, here, if we turn on these two bidirectional switches, then this battery is connected to the LC combination. So the energy will be transferred here. And because it is an LC circuit, the LC circuit causes the current shape like this because it is resonant. So the current shape will be like a sinusoidal. Okay, so when the current rises and return to zero, then we can turn off the switches here, and the energy will be temporarily stored in the capacitor. And then we turn on another set of switches. Then the energy will be transferred back to the batteries by all these switches, selection switches. Okay, by the selection switches, we can transfer the energy from the specific cell to the resonant tank, and then return back to another cell. Okay, so this is also a cell-to-cell equalizer. This is also this is pack to cell or cell to pack, not cell to cell, but it also applies the selection switches. Okay, so the converter here is connected to the whole string, and on this side it is connected to individual cell by the selection switches. And yeah, we can select either one of the switch, and we just transfer the energy from the string to one cell, or from the cell to the whole string. Okay. This is a modularized one. Okay, this is a modularized one, and the hierarchical equalizer also maybe a required one. You know, for the battery pack, the voltage level is is getting higher and higher. For example, at first, for the EV, for the electric vehicle, the battery voltage level at first is only 200 volts. 200 volts. 200 volts means if we think that one cell, because we use the lithium-ion batteries, for each cell the voltage level is around 3.7 volts for one cell. For 200 volts, there are more than 50 cells series connected together, more than 50 cells. But now, the battery pack voltage is increased to 400. Okay, to 400, and the 400 means battery cell series connected is more than 100, and the pack voltage is getting higher to 600 volts. Okay, because you know the power required by the EV is getting higher. When the power is higher, we have two methods. One, either we increase the current, or we increase the voltage. Okay. Of course, we preferred higher voltage, because higher current means higher loss. Okay. So we increase the voltage, and when we increase the voltage level, it is getting more difficult to achieve the direct cell to cell energy transfer. It is getting more difficult. So the hierarchical or modularized equalizer will become required. Okay, for this method, inside this module, there are selection switches. Okay, there are selection switches inside this module. So for the selection switches, the voltage trace of the switches is only limited in the module numbers inside this module. So the voltage level is limited. And for the module switch, the voltage trace is a whole pack. The voltage trace is higher on the module switches, but inside the module, the selection switches for each cell, the voltage trace is lower. Okay, this is related to the cost and related to the reliability. Okay, and then the module is connected to the bidirectional DC to DC converter. So the energy can be transferred between this module to another module. And within each module, the energy actually is directly connected to the individual cells. Okay, so this is called pack to cell or cell to pack modularized equalizer. Okay, and this method makes use of the CEC here. CEC means charge equalization circuit. Okay, it is called CEC, but actually this is a multi-level converter topology. Let's check this first. By the operation of the switches, we can connect all the three batteries into the switch here, into the circuit here. Okay, we can also connect only two batteries to the terminals here. Okay, we can freely select either number of the batteries to connect to the converter to the terminals here. Okay, this is a multi-level converter topology. And so by this method, we can charge the batteries we need to charge. That is, if the battery SOC is lower, then we can shift it out and to charge the batteries. Okay. And this method actually will encounter one problem, and because when we want to charge the different numbers of batteries, that means the output voltage of the DC to DC converter variated very seriously. Maybe the output voltage will be one battery to three batteries. That means the output voltage will be 1, 2, 3 times. So the output voltage range is very wide. For a wide output voltage range converter, it is difficult to design. Okay. It is difficult to design because it is difficult to achieve high efficiency for either output voltage level. Okay, but this method maybe is effective because if we combine the CEC and the DC converter with AC input, if we combine these elements together, maybe this is workable because if the AC input, okay, this is AC input. For the AC input, sometimes the input voltage is low, sometimes the input voltage is high. So if we want to charge smaller number of batteries, we can choose when the input voltage is lower. Okay. When the input voltage is low, then we charge only a small number of batteries. When the input voltage is higher, we just charge more batteries. Of course, we can discriminate the charging time of each battery. Okay. For higher SOC batteries, the charging time should be reduced. Okay. So anyway, we can achieve the balanced state of the batteries. Okay, this is the final category. In this category, we want to control the charging or discharging of the batteries. This is called the battery power module method. And in this method, every battery is connected with one converter. Okay, there is one converter connected to each batteries. This is a buck boost converter. Okay, these are buck boost converters, and they are bidirectional. They are bidirectional converters. So the battery pack can be connected to the load or to a charging source. If we want to discharge the batteries, of course, when the SOC of the battery is higher, then we just operate the converters to discharge more from the battery. And on the other hand, when we charge the battery pack, we just let the lower SOC batteries to get more charge from the charger. Okay. All the functions can be achieved by the control of the bidirectional buck boost converter here. Okay, so this is a energy control method, and this is a hybrid method. That is, actually we have a charger here, and the charger will charge the whole battery pack. Okay, this charger will charge the whole battery pack, but there is one additional charger here. That is a converter. This is a converter, and this is called a priority switch, the flyback converter. And anyway, this is a flyback converter, and by this flyback converter, we can achieve the discriminative charging. for for any one of the cell. The cells can be sifted out by the selection switches if the cell need additional energy because of its low SOC state. Okay, we can use this flyback converter to additionally charge the battery. Okay. Okay. For the charge equalizations, why we can? Well, I have to spend more time on this issue. That is because for the BMS implementation, most of the functions can be achieved by the BMS IC. Most. However, the charge equalization function can only be partly achieved by the BMS IC, and especially the BMS IC can only achieve the balance inside the module. Only inside the module. But for the nowadays battery pack, there are several modules, and we also have to achieve the charge equalization between the modules. There is no direct method. We have to propose our charge equalization circuit for this purpose. And I just introduced the three categories. Of course, the most effective one maybe the energy transfer category. And there are several topologies to achieve the purpose. And you also have to consider many factors, including the pack voltage level. For higher pack voltage level, hierarchical topology maybe should be considered. Okay, because you have to consider the cost. If you want to make the every non-hierarchical topology, the voltage trace of the switches should be high, and the cost is not tolerable. Okay. So the difficulties of the charge equalization will be like this. First, the SOC estimation is sometimes difficult. Remember that last week I introduced one kind of battery, that is lithium iron phosphate battery. Remember that? The LFP battery. For the LFP battery, the feature is it has a very flat voltage range, very flat voltage region. Inside the region, even though the SOC is different, the voltage level is almost constant. So it is difficult for us to discriminate to know the SOC only by the voltage. So for that kind of voltage, for LFP voltage, the SOC estimation will be difficult because voltage is not reliable. Okay, so if you have the experience, we can hear from some news that I heard from some application that the energy storage system developed by some institute, they said their energy storage system developed by the LFP batteries, the service life actually is very short. How short? Only 1 year. It can last only 1 year. After 1 year, the battery pack becomes unusable. Why? That is because the charge equalization failed. Not the cells failed, but the pack is failed. Okay. And for the ternary batteries is better, like NMC or NCA batteries is better, because the voltage and the SOC are discriminable. So for that kind of battery, that is fine. But LFP is very unacceptable. Okay, so this is the first difficulty, and the second is because we don't know which one, we don't know the pattern of the distribution of SOC. Okay, so for our circuit, we have to repeat for every cell. So there are many circuits. There are many circuits inside the charge equalization circuit. Okay, this is the second difficulty. And then the voltage trace, I just said, the voltage trace will increase with the battery number. When your battery series connected battery number increases, the voltage trace for the switches also increase. The cost also increase. The reliability will become worse. And finally is the efficiency. Because the transference, for every transference, it loses some energy. So for the charge equalization circuit, usually the efficiency is not so good. Usually, even though we can apply the self-switching converters to achieve the energy transfer, but because usually it takes several transferences, so finally the efficiency is not good enough. Okay, and the final part is the introduction of the BMS ICs from different manufacturers, and this is the TI solution. TI's for TI, you know TI. The TI they just categorize the BMS into these subcategories. They are chargers, fuel gauges. Fuel gauges means you want to calculate the state of charge and the state of health of the batteries. This is fuel gauge. You know, fuel gauge, just like in the fossil fuel engine car, there is an indicator to tell you that how much oil left in your tank. And for the battery pack, we also need the fuel gauge to tell us that how much capacity left in your battery pack. So it is called the fuel gauge. And then the monitor and the balancer, and finally the protector. Okay.